Okay, folks, my name is Matt Thomas, and thank you for tuning into the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. And for those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, if you're not intending to speak, please just do your best to make sure your microphone is muted and your video camera is off. Ben, thank you for introducing today's speaker.
Thanks, Matt, and thanks once again for organizing this great seminar. It's my great pleasure today to introduce Sabrina Martinez, who's a geologist in the Landslide Hazards Program here at the Geologic Hazard Science Center. Sabrina earned her bachelor's in geology from the University of Houston, Texas, and her master's in earth and environmental sciences from Tulane University in New Orleans. Sabrina's primary interests involve using remote sensing data in conjunction with other analytical methods to help better understand Earth's surface processes. And in the Landslide Hazards Program, she uses this approach to support development of national scale hazard and risk assessments, which she'll talk about today. And also to inform regional scale landslide surveillance and other response efforts. Sabrina is a co-leader on the main task of the National Landslide Hazards Map project. And it's just a real pleasure working with Sabrina. She's always got really exciting new insights, and some of those she's going to be sharing with us today. So Sabrina, please take it away.
All right, thank you for the introduction. So I'm going to get my slides set up really quick here. But yeah, as been mentioned, my name is Sabrina, and I'm a geologist in the Landslide Hazards Program. And today I'm going to be giving a presentation on some of the work that my group and I have been doing on trying to determine variations in population exposure to landslides across the United States. And so before we begin, I wanted to briefly discuss the motivation for this project. As many of you are aware, the National Landslide Preparedness Act was passed in 2021, and the law directs the Department of the Interior to create a program to reduce losses from landslides. However, we know that landslides are complex, and we've learned this from many of the previous landslide hazard seminars. And what I have shown on the bottom of this slide are examples of landslides across the United States from left to right. The first image is a landslide that occurred in 2017 in Big Sur, California. The next photo is a landslide that occurred in 2018 after a magnitude 7.1 earthquake in Anchorage, Alaska. And the next photo shows landslides that were triggered by Hurricane Maria. And finally, the last photo is of the La Conchita landslide in California. And so in just these few examples that I have shown here, we can visually see that landslides in the United States can vary significantly in the way that they are expressed on the surface of the Earth. And whether they occur is dependent on factors that are both static and dynamic, and that can also vary in space. And so because the United States encompasses such a large geographic area with varying climatic and geologic conditions across this area, coming up with a way to reduce losses from landslides is no easy feat. So a first step toward reducing losses includes working towards filling in knowledge gaps regarding landslide hazard and risk across the country. And so today I will be discussing only one portion of this effort to develop national scale products to fill those knowledge gaps. And that's the effort to determine across the country where landslides might impact people. And so as shown here, landslide exposure can be thought of the presence of people or other assets of interest in places that could be adversely affected by landslides. And for this presentation, we're going to be focused on people. And so exposure analysis is only one part of the entire risk picture. As shown in the sketch here, risk is the combination of hazard, exposure, and vulnerability. And hazard can be described as the probability of an event occurring in a given location and over a specified period of time, whereas exposure refers to the presence of people in places that could be adversely affected by an event, like I mentioned previously. Vulnerability, on the other hand, is the combination of physical, social, cultural, economic, historical, and political components that influence the degree to which an individual or a community is susceptible to damaging effects of an event. And so exposure, as illustrated here and mentioned in the definitions, is just one piece of the risk puzzle and can be used to inform loss reduction efforts. And so previous work by Imbers et al. Highlights the utility of exposure analyses for determining where landslides might impact people and how this can vary geographically. In their work, they used NASA's Landslide Hazard Assessment for Situational Awareness Model, which is LASA for short, that's the acronym, and global population information to determine global population exposure to rainfall-triggered landslides. And the hazard model that they use incorporates a static susceptibility map and satellite-based precipitation measurements to determine landslide hazard globally. And the hazard model uses the precipitation information to determine an antecedent rainfall index. And when this index exceeds a threshold, something called a nowcast is generated for a 1 kilometer cell within the model. And the nowcast used in the exposure analysis presented here just simply indicates that within that 1 kilometer cell, landslide hazard is elevated for a 24-hour period. And so to determine exposure in this study, the authors simply multiplied the number of nowcasts per year by the number of people within each square kilometer cell. And as illustrated in this figure, this highlights that there are regions of the world where more people are likely to be exposed to rainfall-triggered landslide hazards. And so in our work, we wanted to take a similar approach, but to focus on the United States and to determine variations in exposure that exist within our country at a higher resolution. And we wanted to do this in a way that wasn't discriminant of landslide type or landslide trigger. And so in particular, what we want to determine for the United States is how many people are likely to be exposed to landslide hazards, where are people likely to be exposed to landslide hazards, when are people likely to be exposed to landslide hazards, and who is likely to be exposed to landslide hazards. And I have an asterisk next to the who because during this presentation, I'm not going to discuss this at length. Rather, I'm only going to provide an example of how exposure analyses can be used to begin to answer this question. And the question is more nuanced than can be addressed in this presentation alone. But as we saw in the previous slide, vulnerability is also a component of risk. So understanding who might be adversely impacted by landslide events is important because it can inform risk reduction activities. Okay, so now that I've given you some background information and context as to why we've carried out this analysis, I'm now going to explain how we performed the landslide exposure analysis for the United States to get at those 4 main questions. Okay, so the exposure analyses that we performed is relatively simple and straightforward, and it relies on 2 national scale models. The first model, of course, is a population model. And this model has coverage for the entire country, which includes Alaska, Hawaii, and Puerto Rico. And it's a 90-meter resolution model that estimates how many people are likely to be in a 90-meter grid cell during the day and at night. The susceptibility model is similar. It's a model that estimates the likelihood of landslide occurrence within a 90-meter grid cell. I'll explain the model in more detail on a subsequent slide, but one thing I wanted to mention here is that this is a susceptibility model and not a hazard model. Unlike the example that we saw using the LASA model to determine exposure, the susceptibility map does not incorporate a component of time. Rather, it's simply a model that estimates where landslides are likely to occur in the United States. So lastly, we combine the derivatives from the exposure analysis using those 2 models with county scale data from the US Census Bureau's American Community Survey. And the survey provides information on demographic variables such as poverty or linguistic isolation at the census tract and county scale. And so for the presentation, I'll only be focused on county level scale data. Then the next few slides, I am going to explain each of these models or data sets in more detail. Okay, so the population model that we used is developed using a method called spatial decomposition. So the inputs into the model are population data that have been aggregated at larger scales, such as US Census data at the census tract scale. And so the model spatially breaks down that information into 90-meter grid cells. And estimates for daytime versus nighttime population are refined by incorporating more information on workers, for example, school children, the prison population, and the transient population. And all of this is coming from sources such as the Bureau of Labor Statistics, the National Center for Education Statistics, and the National Jail Census. And so for the exposure analysis, these population models provide us a consistent and national model of how population is likely distributed across the country during the day and at night. And so, of course, this spatial decomposition does introduce some error into the population estimates. But as shown here, the population estimates from the LandScan model, when aggregated back to the county scale, are in close agreement with the census-derived population values at our scale of interest, which is the national scale. You can see on the right plot, you can see that the values are, for the most part, in agreement. And if you'd like to read more about the population model, the DOI for the associated publication is provided below. Okay, so of course, an important aspect of estimating landslide exposure is knowing where landslides are likely to occur. And so we use a national landslide susceptibility model to determine population exposure to landslides across the United States. And the model that we use in this analysis is an update to previous national scale models. And the updated model describes landslide susceptibility at a 90-meter grid cell resolution. The inputs into the model are 10-meter USGS 3D elevation program digital elevation models and data from the US Geological Survey's National Landslide Inventory compilation. And the inventory is a compilation of over 600,000 occurrences of landslides across the United States that is not discriminant of landslide type or trigger. And the improvements to this model from previous national models include the increase in resolution, the increase in the number and geographic distribution of landslide data to inform the model, as well as the expanded coverage to Alaska, Puerto Rico, and Hawaii. And so the model uses a topographic slope relief threshold to identify landslide susceptible terrain from those digital elevation models that I mentioned. And those digital elevation models have a resolution of 10 meters. So to minimize the effects of uncertainty related to the elevation models, as well as the national inventory data, the model is downsampled from 10 to 90 meters. And so the number associated with each pixel in the susceptibility model and the numbers that you see in the legend here correspond to the number of pixels within a 90-meter grid cell that exceed the slope relief threshold. And so shown here is the susceptibility map on the right. You can see that susceptibility is broken down into these 5 classes corresponding to a range of those pixel values that I mentioned. And these classes, while useful, and I will use them for the remainder of the talk, they don't have any physical meaning and were defined by breaking up the susceptibility pixel values into 5 equal interval bins. And while they don't have any physical meaning, we can still think of them as being generally reflective of differences in susceptibility. And the reason for that is because, as you can see on the plot on the left, if you take a look at the top bar, this is showing the breakdown of documented landslides within each susceptibility class. And we can see that 93% of landslides occur in these 3 pinkish to red classes. And only a small portion of landslides occur in the remaining 2 classes. And so for the purpose of this talk, we'll be discussing exposure in terms of these categories. That is areas or terrain that have some landslide susceptibility and areas that have considerable landslide susceptibility. And so if you have questions about the updated model, you can direct them at Ben Mears, and he's on the call today. I won't be discussing the model in more detail for the remaining portion of the presentation, but if you have any burning questions about this model, please ask Ben about it, and I believe he'll be giving a presentation about the updated model relatively soon. Okay, so lastly, we also use data from the United States Census Bureau's American Community Survey to compare exposure values to demographic information at the county scale. And the summary is conducted by the Census Bureau on a yearly basis using monthly samples, and it summarizes demographic information at the census county and state scale. The information that it summarizes are things such as poverty or linguistic isolation, and you can see an example of that shown in the map on the right. Okay, so now that I have described the models and data that I'm using for the analysis, I am going to give a brief explanation of the workflow used to determine population exposure. The concepts are relatively straightforward, but because we are working at many scales, so it's the county and the national scale, and looking at things in terms of different susceptibility classes, I thought I'd provide a conceptual sketch of how the exposure estimations were done. And so the first thing that is important in this workflow is to align the population grid and the susceptibility grid, which is fairly straightforward. Fortunately, both of these grids are at the same resolution, and that means alignment comes down to resampling one of the grids to the other. And because I'm concerned about population values, I align the susceptibility map to the population grid. And so this is done, like I mentioned, by resampling the susceptibility grid to the population grid. Once the grids have been aligned, the next thing that I do is create individual population grids associated with each susceptibility class. So remember that there are these kind of 5 susceptibility classes, and we're focused on these 2 susceptibility ranges that are broken up here. And so for the individual grids, I convert each population value that doesn't fall into my desired class to a no data value. And so this results in population grids associated with each of the individual classes. So of course, this might seem like overkill and it might seem like it's very inefficient, but in creating these individual grids, it provides a flexibility during the data exploration phase. And so you'll see some of this during the part of the presentation where I present results. Okay, and so once individual population grids associated with specific classes have been derived, the rest of the workflow is mostly basic grid math. I can sum the population values within each class for my desired scale of interest. Say for example, if I wanted to determine the number of people within one class for the whole country, I would simply sum the population values for my desired susceptibility class for the whole country, and using that one grid. And similarly, I would sum the population values for my desired class or class range at the county level if that's what I was interested in. And so once the population values have been determined for the county scale, by summing up that information at that level, we can then combine this information with the American Community Survey data on demographic information, because this data is commonly available in tabular format. And so at this point in the workflow, joining the information is just a matter of organizing and joining data tables. And so an example of that is shown here. After the analysis has been performed at the smallest scale of interest, and in our case, that would be the county scale, a data table like the one can be created. And this data table can then be used to make maps to visualize how exposure varies geographically. It can also be used to perform basic calculations, such as determining the proportion of people exposed in a county. And it can also be used to sum population values for counties that can be defined by some demographic variable from the American Community Survey. So point being is that now that the data is in tabular format, there are many ways to aggregate the information and visualize the results. Okay, so now that I have described the models and information that I'm using for the exposure analyses, I'll be showing you some of the results from this work. And so, as mentioned earlier, what we want to know first is how many people might be exposed to landslide hazards in the United States. Of course, we all have some general idea of how many people might be exposed to landslides based on independent estimates. But in using these 2 models, we can now get at this question for the entire country in a more objective and consistent way. So unsurprisingly, what we find is that most people don't live in landslide susceptible terrain in the United States. 77% of the United States population lives in areas that are considered to have negligible landslide susceptibility. And of course, this makes intuitive sense because most people live in areas that are flat and easy to develop on. Of the people that do live in landslide susceptible terrain, most live in areas with some landslide susceptibility. In other words, 20% of the population within the United States is living in terrain that is considered to have some landslide susceptibility. And then in comparison, only 3% of the population lives in areas with considerable landslide susceptibility. While that is a small percentage of the United States population, that's still over 9 million people. And that is more, just for a frame of reference, that's more than the number of people that live in the state of Colorado. Okay, so this table summarizes this information that I just mentioned, and shown in the last column on the right is the percent of landslides documented from the national inventory within these susceptibility ranges discussed. And so you'll notice that within terrain that is considered to have considerable landslide susceptibility, 93% of the documented landslides occurred within this range. Okay, so now that we have a general sense for how many people in the United States may be exposed to landslide hazards, I'm going to move on to the question of where. That is, spatially and geographically, where do we see pockets of exposure? And how does this vary across the country? And what I have shown here is the population density within a 990-meter grid cell of those living in terrain considered to have considerable landslide susceptibility. And this reflects what we just talked about. Most people aren't living in landslide susceptible terrain at this level. At this scale, you can't see much. You can see that in most places, this population density is less than 25 people within that approximately 1 kilometer grid cell. For Puerto Rico, however, you can see that this differs from most of the country. And throughout the talk, you'll see that this becomes a pattern. And so when we zoom into a few select areas, and these were arbitrarily selected, we can see that population density is clustered around many urban areas, unsurprising. Shown here, we can see clusters of exposure near the Bay Area, within Southern California, and near major urban areas in the Appalachian region of the United States. Again, not an entirely surprising result because more people generally live in or near urban areas, so our exposure maps are skewed to these areas. The same information is shown, that was shown in map form, is now shown here in a bar graph for specific states. And on the left is a bar chart showing the total population exposed within terrain that is considered to have some landslide susceptibility. And you can see that California has the greatest number of people living in landslide susceptible terrain within this susceptibility range. That's the same if we look at the chart on the right for considerable landslide susceptibility. We can see that in this case, though, Puerto Rico moves up the ranks here, followed by some Appalachian states. Okay, so I'm going to linger on this one a little so that you all can look at this bar chart. But in the last few slides, I had been focused on showing you all total population exposed, and we broke that down at the state level too. And so what I have shown here is the information on exposure broken down by each state and each class so that we can get a sense for the proportion of population exposed within each state. And so this paints a different picture than what we saw previously. This plot is sorted from left to right by the proportion values in the considerable susceptible terrain category. So what that means is that West Virginia has the largest proportion of people living in landslide susceptible terrain that is considered to have considerable landslide susceptibility. West Virginia is followed by Puerto Rico, Vermont, Kentucky, Pennsylvania, Hawaii, Georgia, and then Alaska. So now that we've gotten a sense for where people are exposed to landslide hazards, I'm going to briefly touch on the when of landslide exposure. And that's not when in terms of when a landslide is more likely to occur. but when based on how people move throughout the day. As discussed previously, the landscape model gives us a sense for population distribution during the day and at night in the United States. And this is useful in terms of exposure analyses because we can identify how people may move in and out of landslide susceptible terrain during the day and at night. In a general sense, many people are at work or at school during the day, and this is more pronounced in urban core areas, as shown in the example on the left. You can see the kind of dispersion of the population in this area at nighttime. When we look at how exposure varies during the day and at night, we see generally that more people are within landslide susceptible terrain at night than they are during the day. And this is the case for both class divisions. And so within terrain with some landslide susceptibility during the day, there are over 650 million people within this terrain. And then at night, there are over 69 million people in that area. Within terrain that is considered to have considerable landslide susceptibility, there are over 9 million people in susceptible terrain during the day, and then over 16 million people in that same area at night. When we break this down by state, we see that California has the highest number of people within landslide susceptible terrain at night than during the day, followed by Pennsylvania, Tennessee, Georgia, North Carolina, Puerto Rico, Washington, and Virginia and West Virginia. And you can see that in map form as well. Okay, so now we are going to move on to the who of landslide exposure. So who is exposed to landslide hazards in the United States? And again, I have that asterisk here, as mentioned previously, because I'm only going to be providing one example of how to get at this question. This question is much more nuanced than I can convey in this presentation, but I think it's something important and it's something that we should consider and maybe discuss. So why should we think about who is exposed to landslide hazards? So here I have a quote from a review on poverty and disasters in the United States that states that the poor are more likely to perceive hazards as risky, less likely to prepare for hazards or buy insurance, less likely to respond to warnings, more likely to die, suffer injuries, and have proportionately higher material losses, have more psychological trauma, and face more obstacles during the phases of response, recovery, and reconstruction. And so this excerpt illustrates that how people perceive, prepare for, respond to, and recover from landslide events likely varies across the country. And in this case, unfortunately, can vary depending on your income. And that's something that we don't have a consistent national picture for in terms of landslides. And so exposure analyses cannot answer this question and fill that knowledge gap, of course, but it can be a starting point for research efforts that can then be used to inform risk reduction or loss reduction activities. And so what I have shown here is an example where I have taken counties that have what the US Census Bureau defines as a county with a high poverty rate and determined the number of people exposed to landslides within those counties. And so we see that Puerto Rico, followed by Kentucky and West Virginia, have the largest number of people that fall into these two categories of exposure and living in a county that's considered to have a high poverty rate. Puerto Rico, Kentucky, and West Virginia also have the largest proportion of people in terrain with considerable landslide susceptibility and who are also living in a county that is considered to have a high poverty rate. Okay, so I've shown you all of the results that we've gotten from the population exposure analyses individually, but now I'm just going to summarize those findings here. So for this question of how many people are likely to be exposed to landslide hazards, what we found is that roughly 1/4 of the United States population may be exposed to some type of landslide hazards, and approximately 3% of the population are living or working within terrain that has a considerable level of landslide susceptibility. Again, that's over 9 million people and more than the population of the state of Colorado. And so where are people likely to be exposed to landslide hazards? Our results reveal regional disparities across the US between proportional and total population exposures. And this does have implications for risk reduction activities. For example, California has the greatest amount of population exposed, while West Virginia has the largest proportion of their population exposed. And in terms of when are people likely to be exposed to landslide hazards, what we find is that more people are likely exposed at night, which likely reflects the greater number of private residences exposed to landslides versus schools and places of business. And this also potentially reflects where the economic burden of a landslide disaster might land. And in terms of this question of who is exposed to landslide hazards, for our example, where we use the American Community Survey information, what we found is that roughly 5.5 million people are exposed to landslides that also live in a county with high poverty rates, which reflects that some areas, so for example, West Virginia and Puerto Rico, these areas are at a disadvantage in terms of recovering from major landslide disasters. And so some food for thought. And so these are just some questions that I put on this final slide to hopefully spur discussion. Obviously, it's not an exhaustive list of questions or considerations that come out of this work, but these are things that were on the forefront of my mind. What we found is that millions of people in the United States may be exposed to landslide hazards, and this number increases at night. So can the exposure information inform monitoring and research priorities? Can it inform residential development with increasing population growth and expansion? Additionally, the findings highlight knowledge gaps on landslide impacts. In particular, how does income or any other demographic criteria affect people's ability to prepare for, respond, and recover from a landslide event? And how does this vary across the country? And so those are just some questions to spur discussion. And with that, I'm going to put back the findings slide so that we can have that for consideration during the Q&A. But yeah, thanks for listening.